All right, let's jump right into this explainer. We are a light in the middle of a massive shift in software engineering. We're talking about leaving behind those old, passive autocomplete tools and moving straight into the era of third-generation autonomous command line agents. But, as you've probably guessed, orchestrating these incredibly smart agents comes with a massive headache. So today, we're going to explore exactly how modern systems engineers manage these tools without completely blowing out their cognitive budgets.
And honestly, it's a serious question. How do you keep an autonomous agent from just losing its mind? Picture this. You've got a top-tier coding agent, maybe Google's Antigravity CLI or Anthropic's Claude Code, and you've tasked it with a massive codebase refactor. It's analyzing files, it's running tests, checking logs, and then suddenly it gets stuck in this infinite failure loop. It just keeps trying the exact same broken solution over and over again. Why? Because its memory is so bloated, it's literally lost in the noise. I mean, it's basically the AI equivalent of a complete mental breakdown.
So what's actually happening here is a phenomenon known as context decay. Look, every AI has a strictly finite cognitive budget, its context window. And you know how it is when we get a little lazy and just dump every single API doc, utility script, and massive raw log file into a prompt? Well, the agent suffers from rapid context decay. It literally runs out of brain space. It has to start compressing its earlier instructions just to fit the new stuff, and its ability to reason just falls off a cliff. Which basically leaves us looking at two completely different approaches. On one hand, you've got your standard classic workflow, dumping absolutely everything into the chat and just crossing your fingers. And on the other hand, you have context engineering. This is all about enforcing strict cognitive boundaries. If you're working with advanced systems, you absolutely have to take this clean, deterministic approach. Otherwise, they're just going to drown in their own context bloat. So, how do we fix this? Well, to solve this bloat and keep that active context container super clean and low on tokens, engineers are turning to a declarative framework called SKILL.md. Basically, instead of overwhelming the agent's baseline memory by front-loading every tool it might conceivably need, we give it a highly structured way to pull in domain-specific knowledge, but only exactly when it needs it. This right here is built on a brilliant concept called progressive disclosure. To really visualize this, think of a physical developer's workspace. If you just keep every single manual, screwdriver, and loose file piled high on your main desk, you're not getting anything done, right? You can't find a thing. Progressive disclosure gives the AI a perfectly clean desk. But underneath that desk, it's equipped with these sleek, highly organized modular drawers that only pop open when a very specific tool is required. Let's walk through exactly how this modular drawer system protects that finite memory space. First, a specific task triggers a tool. Then, a highly targeted skill drawer automatically slides open. Once it's open, it injects its specialized schemas and executes the procedure locally, right inside a sandbox. And finally, and this is the absolute magic of it all, the drawer shuts cleanly. Only the finalized, neat little summary gets passed back up to the active context, meaning you instantly reclaim all that precious token space. Now, I know that sounds like magic, but it's actually just a declarative markdown file. You can think of a SKILL.md file as a hyper-specific instruction manual. It lays out the basic stuff, like the name and description, but more importantly, it defines the precise tools needed, the exact execution steps, and the triggers. And those triggers can either be manual, like a human firing off a /command, or completely auto-detected by the agent itself. To put this into perspective, let's look at a real-world example. A database migration audit. Imagine you're working away and you modify it a SQL file. Boom. The skill auto-detects it and triggers instantly. That specific skill drawer slides open, the agent runs all its schema inspections in the background, flags any missing indexes or hazards, and then snaps the drawer shut. And it does all of this heavy lifting without cluttering up your main, active reasoning session with thousands of lines of raw SQL logs. So, by strictly separating that active reasoning context from the modular skills storage, the agent's active memory stays lightning fast. It stays totally deterministic. Protecting that active context, that is the absolute secret sauce here. That's what allows an agent to actually maintain deep, multi-file reasoning over a super long coding session without completely losing the plot halfway through. All right, moving on to system-level orchestration. Zooming out from the individual skill drawer for a second, let's see how this actually fits into a broader multi-agent architecture. The Google Antigravity ecosystem is a prime example of this. Whether you're wrangling a bunch of repos in the Visual Desktop GUI, or you're running headless scripts over SSH in the terminal, or even using the Python SDK, they are all sharing the exact same underlying execution harness. And yep, they are all bound by those same strict modular skills.
Under the hood, the system is executing a really rigorous multi-phase loop. It kicks off with context assembly, basically gathering up the baseline state of the project. Then it moves to planning, where it actually generates structured artifacts for you, the human, to review. Next up is tool invocation, where it reaches out and interacts with the file system. And finally, verification loops, because we all know AI can hallucinate, where it actually runs your test suites to double-check its own work before calling it done. But to govern a loop that powerful, you really have to step up and play the role of systems architect. You're the one fine-tuning the parameters based on the task at hand. You've got sandbox isolation, which gives you OS-level containment so untrusted code doesn't wreck your machine. Then there's the autonomy level, which dictates whether the agent needs your explicit permission before applying a file diff. And of course, the thinking budget, where you allocate hard token limits for when the agent is trying to untangle a really nasty, deep-rooted bug. Of course, even the best agents can and will get stuck. Say an agent fails a test, tries to fix it, fails again because of some obscure missing dependency, and suddenly, bam, it's locked in a death spiral, just burning right through your API budget. That is exactly why setting strict iteration caps, what we call mandatory loop circuit breakers, is absolutely critical. If the agent fails, say, 5 times in a row, the breaker trips. It cuts the power, reverts the state, and immediately flags you to step in. Now, if you're dealing with massive, enterprise-scale tasks, one single agent just isn't going to cut it. You basically need an entire corporate org chart of AI. You'll have a lead orchestrator delegating work across a few different topologies. You've got hierarchical structures for your classic boss-to-worker tasks, horizontal setups for peer-to-peer code reviews, and Blackboard architectures where multiple agents are working asynchronously, reading and writing to a shared global state. But here is the kicker. No matter the topology, every single worker agent stays perfectly isolated inside its own strictly managed context window. So practically speaking, how do you manage the sheer risk of an autonomous agent just totally nuking your code base? Well, when you initialize a new project, say you're in Antigravity 2.0, you definitely don't want to just let the agent loose on your main branch. Instead, you can boot agents directly into new worktree mode. This spawns a completely isolated Git worktree. It lets the agent test out massive, highly destructive refactors safely without ever polluting your actual active working directory. What we are looking at here is a fundamental paradigm shift in software engineering. We are steadily moving away from legacy engineering, sitting there manually typing out boilerplate syntax line by line. We're moving into the era of terminal native orchestration. In this new world, your primary job shifts. It's now all about defining intent, specifying architectural invariants, and supervising these autonomous workers. Frankly, you are no longer the typist. You are the architect. And the efficiency gains? They are just staggering. By fully embracing progressive disclosure and using deferred tool loading, enterprise environments are saving up to 191,300 tokens of context space per single session. I mean, think about that. That isn't just a nice little cost saving on your API bill. Preserving that many tokens is literally the difference between an agent successfully completing a complex refactor or just completely falling apart due to context decay. Which brings us to a critical question to wrap up this explainer. As these agents start taking on more and more operational burden, you really need to look at your own workflows. Are your systems actively engineered to protect the fragile cognitive budgets of your AI tools? Or are you just dumping a mountain of noise onto their desks and hoping for a miracle? The future of software engineering is going to belong to the teams who master the agent token economy. Thanks for hanging out and exploring this with us.